Okay, so let's look at the second part of this. So in the first part, we figured out what was the transfer function that would tell us how to get from Vn to V sub c and how to get from In to V sub c. So this was what we said. Now the total result is whatever the Vn component is plus whatever the In component is. So let's just write this guy as h1 Vn of s plus h2 Vn of s, or sorry, In of s. Okay. And to be clear, I should probably say h1 of s, because h1 and h2 are also functions of s, like this. Okay. Now, if I want to figure out what the time domain waveform is, what I've just solved for here is what the transform of the time domain waveform is. Our goal, as we wrote at the very beginning, was to figure out what is V sub c. Okay. Now, in the special case where we have sine waves like this, we don't need to do the Laplace transform analysis. Okay, that's what we've already said. So let's look. We've got our two inputs. Vn of t is 10 cosine t plus 30 degrees, and In is 3 cosine t minus 30 degrees. Okay, what we're going to say is these guys are really just like complex exponentials. Let's say this guy is the real part of 10 e to the j 30 degrees times e to the j t. Okay? And the way you could see that is if you expanded this out, you would see that's the real part of 10 and e to the j 30, e to the j t, I could write as e to the j t plus 30 degrees. And that is the real part of 10, and then you expand it, cosine t plus 30 degrees plus j times 10 sine of t plus 30 degrees. And clearly, the real part of this expression is the same as the original input. All right, so similarly for In, I could say that this is the real part of 3e to the j negative 30 degrees times e to the j t. Now, one thing I want to point out, if you look at this 10 e to the j 30 and 3 e to the minus j 30, those are the same as the phasors that are associated with these guys. So 10 cosine t plus 30 degrees, the phasor would be 10 angle 30, or equivalently 10 e to the j 30. And this guy would be 3 angle negative 30, or 3 e to the negative j 30 degrees. Okay, so those guys are entirely equivalent. Okay, all right, so all that said, what we've done is we've put V in terms of complex exponentials and I in terms of complex exponentials. Well, if our interest is, as we have always said, with the steady state component, okay, we're really interested in the steady state component. What we've said in the past is that if I have a system, h of s, and I have some input, call it x of s, and some output, call it y of s, okay? Well, what I find is that if x is, just to be clear, if the time domain waveform is some x e to the s naught t, then the output here, y of t, the time domain output, is h evaluated at s naught times x times e to the s naught t. Well, I have a similar thing here. Basically what I'm saying is that the inputs are essentially the real parts of complex exponentials. So that means that the steady state output here, all right, the steady state output is going to be, in this case, the real part of h1 evaluated at s naught t. So in this case, our s naught is j times 1 times 10 e to the j 30 degrees times e to the j t. Okay, so if I simplify that here, so what's h1 of j1? Well, I'd have to calculate that. So h1 was this expression here. All right, this is h1 of s, and I would need to plug in s equal to j1. All right, plug that in, it becomes a complex exponential, right? I get 18 times j plus 45 all over 18 times j squared plus 45j plus 18, okay? That needs to be simplified. So basically this has two results to it, right? It has a magnitude and it has an angle, okay? Now, similarly, for this guy, I would have that v sub c steady state from this guy would be equal to the real part of, in this case, h2 of j1 times 3e to the minus j 30 degrees times e to the jt. Okay, so to solve this, I need to know what h2 is at j1. Okay, so to solve that problem, what I'm going to do here is I wrote a piece of code where I plugged in R1, R2, L, and C. And then I wrote my H1 here and my H2 here. Now notice what I did. I said omega equals 1, that's our frequency. S equals j omega. And then here's my H1 expression. Here's my H2 expression. And then I do abs and angle like that. So what I'm going to do is going to right click on that, evaluate, and I see that I get these numbers right here. So in this case, what I find is, so notice I know the order of these things. This is the magnitude of H1, this is the angle of H1, this is the magnitude of H2, this is the angle of H2. So I'm going to write this like this. The real part of, so H1 is 1.077 e to the negative j 68.1986 degrees, okay? And that gets multiplied by 10 e to the j 30 degrees, and that gets multiplied by e to the jt, okay? Similarly, for this component, the in component, I get the real part of, so what is H2? H2 is 0.0667 with an angle of negative 90, so I say e to the j negative 90 times 3 e to the minus j 30 times e to the jt, like so. Okay, so in this particular case, if I say, well, how do I simplify that? Let's get this out of the way here. Okay, that's the real part of 0.067 times 3. So 0.0667 times 3. So I'll just round that to 0.2. And the angle looks like it's e to the minus j 120 degrees times e to the jt. So that simply becomes that this is 0.2 cosine of t minus 120 degrees. That's the component of the output that exists from the current source. If I'm looking at the component of the output that comes from the voltage source, it's the real part of 1.077 times 10. Well, if I do that, that should become 10.77. And my angle here is going to become, okay, I should be able to do that in my head, but just to make sure that I'm right, 1986 plus 30 degrees. So I took negative 68.1986, added it to 30, and I get negative 38. So e to the negative j, negative 38.1986 times e to the jt. So that becomes, in other words, if you expanded this with the Wither's identity, took the real part of that, you would get 10.77 cosine t minus 38.1986 degrees. To do that, again, you'd have to remember that you'd have to expand this with 10.77 cosine plus j times 10.77 sine, and all of that, right? You'd have to remember your Euler's identity. So what we're ultimately saying is that the steady state component, the overall steady state component, is 10.77 cosine t minus 38.1986 degrees plus this guy here, so 0.2 cosine t, and I believe it's minus 120 degrees. Okay. Now somehow those can be combined using a trig identity if you really wanted to get one cosine, but you don't have to. Just know that the first term comes from the Vn, and the second term comes from the In.